This is part 2. I've tried to make this video a number of times and it's not very successful. So what I'm going to go down to is this. I am going to put all 3 of these molecules, drawing their Lewis structure, on this slide and write for you the number of bonding and non-bonding. Each of these has 4 electron domains. When I look at methane, there are 4 electron domains. When I look at ASO3, all right, when we have our lecture Zoom, I will definitely go into more detail. It has 4 electron domains. And when I look at water, which we have drawn a number of times in our class, it has 4 electron domains. What's the difference between them? Well, methane has 4 bonding, 0 non-bonding. Arsenate ion has 3 bonding, 1 non-bonding, and water has 2 bonding and 2 non-bonding. So again, insight. There's a lot of work that goes into drawing these, but I've lost the message as I try to present this. All of these have electron domain geometry that is called tetrahedral. What happens with their molecular geometry? That's where there's going to be a change. Methane is going to have the tetrahedral. When we look at the arsenate, let's just say it's a lot like NH3, make that connection. We're going to say that it is trigonal, and we will say it is pyramidal. And then when we look at water's molecular geometry, we're going to say bent. And this is how I normally do it in the classroom. I'd write the whole thing on the blackboard so you could see the big picture at the same time. So we've knocked off our molecular geometry. We know our electron domain geometry. We know our number of electron domains and our number of bonding and non-bonding. The last thing to talk about is polarity. Methane is nonpolar. Arsenate ion is polar due to that electron pair. And water, we definitely know is polar. So I reduced all 4 electron domains to 1 slide. So that's 4 electron domains. Okay. The next one I want to talk about is 5 electron domains. And that would be the mother AB5. And it's going to be where 2 trigonal pyramids share a base. What do I mean by that? Well, I'm going to draw this triangle, and I'm going to put a B here, a B here, a B here. This is in the XY plane. I'm going to put my other elements that make this up on the Z axis. So now if you read what it says, the ones that are called equatorial, 3 pairs in the plane. We have a BBB, each of them is a covalent bond. The axial, there's a pair above and a pair below the plane. They are on the Z-axis. Now, the thing you're not going to expect, and this is also what kind of confuses students, is whenever we're going to have electron pairs, they're always placed in the equatorial position. Think of the Earth's equator, kind of bisects our Earth in half. Think of the axis, think of that as the Z-axis. Okay, so let's do some examples now. I'm going to just draw the structures. I've been doing this one a number of times and I cannot get it to really work. So I'm going to draw the Lewis structure for PF5. I'm going to put in all the electrons and I'd like you to try it on your own. Again, watching me is not going to help you learn it. You got to try it by yourself. We have these 5 electron domains. We have 5 bonding, 0 non-bonding. So our electron domain geometry has the word trigonal, and then it says bipyramidal. And I'm going to abbreviate that as TB, trigonal bipyramidal. When we look at our molecular geometry, it's going to be the same, trigonal bipyramidal. When we try to do the polarity, we're going to find that each of the bonds is pulling equally, and this will be a nonpolar molecule. Again, I'm leaving the Lewis structures up to you. Got to fit it into this YouTube video. For my next one, I don't think I can do that. For my chlorine tetrafluoride ion, I have 7 plus 4 times 7 minus 1. I have a grand total of 34 electrons. I'm just going to draw it. I'm going to put the Cl here, my fluorine, my fluorine, my fluorine, my fluorine. And when I'm all said and done doing all the electrons around the fluorine, I'm going to have 2 electrons left over. And as we said, they're going to go into the XY plane. So sure, we have 5 electron domains. That will give us an electron domain geometry that we are calling trigonal bipyramidal, but we have 4 bonding and 1 non-bonding. So our molecular geometry, it's not going to have the same name. It is going to be called seesaw. So that's the part, well, you have to learn all of this. I'd love to say there's just a little bit to learn, but there's a lot to learn. Remember, this is Lewis that we did in Chapter 8. This is Lewis that we did in Chapter 8. What we're adding in here now is the VSEPR. And what is it going to do to angles? Well, these 3 that are in the plane, if I draw it like this, fluorine and fluorine, it is going to push this and it's going to draw this together. So this will be less than 120. This will be greater than 120 degrees. And what is this molecule going to be? This molecule is going to be polar because of that lone pair of electrons. Went too far, is ICl3. 7 plus 3 times 7 is equal to a grand total of 28 electrons. And again, I am simply going to draw it. I've recorded this so many times and it just gets too long. Here's a Cl, here's a Cl, here's a Cl, and there are my 2 lone pairs. So work it out. Make sure you can account for these 24 electrons, and I'm going to focus on what this section is teaching. We have 5 electron domains, and we're calling this trigonal bipyramidal. We have 3 bonding, 2 non-bonding, and that is going to give us, for our molecular geometry, that is being called a T shape. Again, I did not make up the words. Don't shoot the messenger, okay? And when you look at this, we've got those 2 lone pairs. This is definitely going to be polar. So you may be thinking, oh, anytime I have a lone pair of electrons, I will always be polar. Our next example, well, this last example will tell you that's not always true. This should say XEF2. And essentially what we have is 8 plus 2 times 7. And we have a grand total of 22 electrons. And I'm, again, just going to draw it. I have xenon, and when I have 5 electron domains, I tend to fill my axial position first. When I put in all my electrons, and again, I'll let you do that, what I find is that I have 3 lone pairs left over. And they're all going to go on the x-axis. That's xy, well, x-axis, not really x-axis. They're going to go on the xy plane. I think of it as an x-axis. And we have our fluorines on the z-axis. So what do we have? We have 5 electron domains, and that says that we must be trigonal bipyramidal. But so our electron domain geometry is trigonal bipyramidal. But when we count our bonding and non-bonding, we have 2 bonding, 3 non-bonding. That is going to give us a molecular geometry that, believe it or not, is linear because it's just the XEF on a straight line. And what's going to happen now? Well, what I have is a xenon with 3 pairs of electrons all in the XY plane. They're going to cancel each other out, and that will make this a nonpolar molecule. So to be honest, 4 electron domains, not too bad. 5 electron domains, takes a little bit more work. While I took shortcuts here in order to do this, your first step should always be counting the number of electrons, okay? Once you get the number of electrons, your second step is to draw the Lewis structure. Your third step is to figure out the bonding versus non-bonding, and then use the chart. Use it. Don't try to do it on your own. Pick up that chart, okay? So good luck on this. It is challenging. I am not an inorganic chemist because to me, I'll do this, but it doesn't get me really excited.